Hello, my name is Roberto Costas, and I'm going to give this talk about totally positive matrices with respect to a tree. This is part of a seminar. This is a seminar part of this meeting called CompumatG 2022. I would like to start thanking the organizers to let me give this talk. And as you see, the title is a way to relate matrices and graphs or trees, which are a particular case of graph. As you see, also my slides are going to be in Spanish, and I'm going to give the talk in English just to have a wider people to receive the talk and understand it. So the content is all about matrices and graphs for one side, and for the other are about which cases did we already solve about this particular topic. So let me start giving a basic background about matrices. So the first thing is when a matrix is totally positive, so we are going to call TP matrix for that. So that means that every minor of the matrix is positive. Remember that a minor is just any box of any size less or equal to the size of the matrix. Like in this case, we have a 3x3 matrix. Okay, so this matrix is TP, which means that every minor, so for instance, every entry is a minor. So every entry is positive. Every 2x2 matrix has positive determinant. So for this reason, it's TP. Of course, the whole matrix needs to have a positive determinant. This is for TP matrix, totally positive matrix. Now, a weaker condition is when it's a P matrix. So P matrix is where only the principal minors are positive. The principal minors are those minors which contains the elements of the diagonal of the matrix. So we only need to have 1, 3, and 7 positive. So I don't care about these 3 numbers and about all these other 3. So I only need these 3 number positives. Then this minor to be positive, this minor to be positive, and 1, 3, 1, 7 also have a positive determinant, and then the whole matrix need to have a positive determinant. So if it's TP, it's P matrix, but P matrix doesn't imply totally positive matrix. Now we're only interested about the cases where, kind of certain submatrices of a TP matrix. So we really don't need to have a TP matrix at all. We only need to have TP for some particular minors of the matrix. So we are going to assume that we have a set of numbers 1 to n. This is the set of the matrix, n by n matrix. So we're going to have alpha and beta, any indices in the 1 n set, such that both has the same size, let's say k. We're going to denote A bracket alpha beta like the submatrix of A, for which we have the rows with the indices alpha and the columns with the indices beta. Right? We're going to call, well, as we can see, in this particular case, A231, well, hold on. So we also denote the A parenthesis alpha semicolon beta, like the submatrix where we eliminate, in this particular case, the rows named by the index alpha and the columns from the set beta, right? So for example, if we take A2312, we eliminate the second and the third row. So we eliminate these 2 rows and the first and second column. So we only have the remaining element is 3. So like if we have the bracket case, so the bracket case is just A bracket 2312 is we have the second and third rows on the first and second column. So it's this 1, 3, 1, 4 matrix. Okay. Then of course, if both indices are equal each other, then we just remove one of them because it's simple to remember that. Okay. Now, let's talk about the Sylvester identity. This is a very nice result. So what we do is we take any two indices, alpha and beta, and the determinant is just is like this. So where alpha prime is, we remove the last element of the index alpha. Remember that the elements in alpha are sorted, they're ordered. And beta prime, it also means we have beta, but we remove the last element. Prime alpha means we remove the first element. Here also we remove the first element. Here is we remove the last of alpha, we remove the first of beta, and so forth. And prime means we remove the first and the last element in the for the index, right? So for example, in this case, we have alpha and beta equal 1, 2, 3. Then alpha prime is we remove the 3. Prime alpha means we have 2, 3, and prime alpha prime means just the element 2. So if we want to compute the whole determinant, what we need to do is compute the first 2 by 2 minor times the 2, 3, 2, 3 minor minus 2, 3, 1, 2 minor times 1, 2, 2, 3 minor over the whole thing 3. Okay, which is the 2, 2, and 3. So in this way we can compute this determinant. Okay, another identity which is really useful, it's very simple to remember, is if we call A tilde like the adjoint of the matrix, not the inverse, but just without the determinant. So you remember that A tilde is just A tilde A because it's up to the determinant is the inverse. So then, of course, A tilde equal A tilde A equal the determinant of A times identity, right? This is a standard identity for matrices. And of course, because we have a TP matrices in general, this determinant is going to be positive. Okay, so A has inverse. All right, so let's talk now about graphs. So in particular, we're going to talk about trees. So a tree is just a set of vertices and edges. As you can see, these black dots are the vertices of the graph, and the edges are just the way to connect different vertices, right? As you can see. So now it's important to notice that the height, how do you call that? Well, I mean, the amount of connection is called the connectivity of the vertex. So in this case, that has a connection 5, that has 1, 1, and 1, 1, and 1. So when this number is 1, it's called a leaf, like in a tree, right? So if we remove that, this is just disappear. This is a leaf for the tree. So we have 2, 3, 4, 5, 6 leaves right here. Okay, in particular, we are not interested in any kind of result about the graph, but just edges and vertices. But because we're going to consider matrices, we want to have some particular numbers for each vertex. It doesn't matter the order of these numbers, so you can choose the one that you prefer. Like in this, right? I just said 1 here, 2, 3, 4, 5, 6, 7, 8. This graph has 8 vertices. It's a tree, as I said. Remember, a tree is a graph which no cycles. Okay? There's no cycles here. So you cannot, if you want to go from the 4 to the 4, the only way is going in one path and then come back. You cannot go around any other way to this particular element in the tree. Okay, in particular, the problem we're really interested is about matrices related with the graph. So what we're going to do, you see, even I'm not really much interested about these numbers. Of course, I need the numbers, but what I need is some kind of sign pattern in the problem. So the way to do it is the following. So I'm going to choose one element, okay? Let's say this. So every element that is connected with this element directly is going to have different signs. So if you have minus, it's going to have plus. So every element that is connected with plus is going to have minus. So you see minus, 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 minus. And then for this, because this is minus, those are going to be pluses, right? So we need for one side the labels and also as well the signs of this tree. So probably you can see that it doesn't, you have different labels for these numbers, but this is just this or the opposite, right? The plus here, negative, positive, 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 right? This is the only two ways to do it. You can just say the height vertex, the vertex to be positive, like this one, or negative. You can choose the one that you prefer more. Now, so let's introduce the problem. So the problem is just the following. So you give me one tree, okay, T. You give me a matrix which is TTP with respect to this tree. Now I'll tell you what exactly that means. Now, that means that if we set every path along the graph, this path, let's say for instance this case, yes, this case, so we have the path 1, 2, 4, right? 3, 2, 4, which we are going to order, so it's going to be 2, 3, 4. We have the path 4, 2, 5, 6, so this is going to be 2, 4, 5, 6. Now we also have, of course, 2, 3, 2, 5, but this is included in 3, 2, 5, 6. So we are going to just take the maximum paths, let's say. So we have a covering of the graph. So it's going to be like 1, 2, 4, 3, 8, and then and then 4, 2, 5, 6, and then 2, 5, 7. You can choose all these possible paths, and for each path, for instance, if we take 2, 3, 4, that means that the submatrix with indices 2, 3, 4, 2, 3, 4 is TP. Okay. Now also the minor 2, 3, 4, 1, 2, 3. This is another minor of the matrix. Is going to be also TP, right? So for every path you have, right, you have a set of paths. So every possible element of the way alpha, beta, where alpha and beta is a path of the matrix, is TP. So if that happens, then if we consider the minimum eigenvalue of this matrix A, and that is going to be, in general, we don't know if it's going to be positive or negative, but it's going to be unique, single, then this eigenvalue has one eigenvector related, right? So this eigenvector is going to have this sign pattern. So for instance, in this way, it's going to be negative, positive, negative, 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 positive, positive, negative. This is going to be the sign pattern for this eigenvector, right? If we decide this particular labeling for the matrix, for the graph. Okay, so things that we know. Well, this, by the way, this is a conjecture, so we only have the solution for some cases. There are particular matrices which are TP, for which this result is not true. So this conjecture need to be rewritten or reconsidered with different conditions. But for some particular cases, it works. Okay, so the first thing is every entry of the matrix need to be positive, because each entry of the matrix is part of the path, right? This 2 is part of the path, 3 is part of any path, of some path. So every entry of the matrix need to be positive. At the same time, so all the numbers are positive. Now at the same time, all the eigenvalues are real, positive, and different. Okay, different each other. So this is a thing that we know because the matrix itself, the way it's constructed. If you want to know something more about this, I can show you some particular reference about this. And finally, the maximum I mean, the maximum eigenvalue is also unique. It's called the Perron eigenvalue, and this is all the time positive. Okay. All right. So let me show you which cases we already know that the conjecture holds for them. So the first one is we're going to talk about the 5 stars, the 5-star graph. Well, it should be the 4 stars, right? So you have this case. Okay. So in this particular case, we have this sign pattern. I'm going to take this label, this labeling for the matrix. So you see my A is going to have 1, 2, 3, 4 is size 4 by 4, and we know that the minor 1, 2, 3, 1, 2, 4, 1, 3, 4 are positive, are TP, right? But for example, I don't know what happened with this with the minor 2, 3, 4, right? Because 2, 3, 4 is not part of this this matrix. I mean, it's not a path of this graph. All right. So we expect to have the sign pattern of the eigenvector associated with the minimum eigenvalue to be positive, negative, 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 or negative, positive, positive, positive. This is what we expect. Okay. Okay. So let me start saying that all these positives we already know. Why? Well, let me start with this. This is the adjoint matrix. So this is what I do for the 2, 2 is I remove the 2, 2 entry. So we have 1, 3, 4, right? So 1, 3, 4 is here. So 1, 3, 4, 1, 3, 4 is part of this matrix. So this determinant is positive, which means this entry is positive. So you can do the same thing with this. Okay, it's quite easy to understand, to see that. And the same with this. So these 3 elements are positive. Now this element is the element 2, 3. So we remove the element so it's hold on. So it's 2, 3. So we remove the element 3. So we have 1, 2, 4, which is part of the path. And then if we remove 2, we have 3, 1, 4, which is also part of the path. So this is going to be positive. So then we have positive, positive. Well, we have positive, 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 and then by using that all the paths going along 1, then all these entries are positive. Okay. Now, if we use now the property that A tilde A is the determinant A times identity, that means that this matrix is going to be like the determinant in these entries, and then you have the rest of the elements are 0, right? 0. All right. So if this is A tilde and we already know these values, can we say something about these question marks elements here? Well, yes, because A tilde A is identity except this constant identity, right? So, and because A is entry-wise positive, then if we multiply like this row, the second row, by the first column of the A, is going to be positive, and then these entries you don't know, but the result needs to be 0, which means that this number needs to be negative. So that negative plus positive can be equal to 0, right? So this entry needs to be negative. The same way we have this number and the same way with this number. Just using, let's say, the second row of this matrix times the first column of A. The same thing with the third row from A tilde and the first column of A, and the fourth row of A tilde and the first column of A, in this way, right? So the entries of this product need to be 0, so then these 3 numbers need to be negative. Now, it's by symmetry, or you can just use A tilde equal identity, and these 3 numbers are going to be negative. Okay, so you have negatives in this, but the same, if we use the first row of A tilde times the second columns of A, because now you have minus, 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 this entry needs to be plus. Okay, it's just a question of using properly this identity. So this is the proof, right? So A tilde has the right sign. You can see we are expecting to have that. So plus, minus, 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 and the rest of the elements plus, and it's what happened. And the basic idea is this part is because the graph, and this information comes from the fact that the product is identity. Okay, so now in order to do the start with n edges, let's say, then we have, you see, we have 1, 2, 3, 4, and more, even more, but then you have n, so all of them are leaps except the center, which is a high degree vertex. So we expect to also to prove that it has this pattern, this sign pattern. This plus means all the block respect, you see the leaps 2, 3, 4, 5, 6, and so forth that we have. But by using the same argument, this is going to be positive, right? Because the same idea we had before. So you can see that every element, every entries of this A tilde is going to be related with these elements, and because of that we have the right sign. Now, because A tilde is identity, you have all these minus here, but then by symmetry you have all these minus here, and then you have this is this positive entry. So it was really easy at the end. But we spent some time trying to understand how that works. Now that looks easy, but we spent about, I don't know, 3 months to figure it out. We tried to avoid, or we didn't know that like this tool at the time. All right. Now, if we try to use this technique for some other cases, you will see it doesn't work. So that kind of technique only works for really basic cases like this. So the last case I'm going to show you is enough general, but still you can see that you can consider some other cases which are not included in this talk. So we have a tree, and we have the associated matrix A, which is a TTP matrix, and we have two conditions. So the first condition is that the determinant of A is going to be positive. This is really important. And at the same time, if we remove every leaf P, then this matrix, so the matrix where we remove this P is a P matrix. So every principal minor of a P has to be positive sign. Okay, so under these conditions, which probably you can see they are not so strong, the matrix has the right sign for the eigenvector related with the smallest eigenvalue. Okay, so you see this is nice. By the way, that even this result probably includes the previous cases. So I just decide, well, but in the stars sometimes this determinant is negative. So this is more general, by the way, of course. Okay, but you can see that there are situations which are bigger than the stars, but smaller in conditions. Like, for instance, if the determinant is negative, then you need to probably change the way you have the proof if it's possible to get. So let me show you this case. So you have this tree, okay? This tree, so you see it has 10 vertices. I label in this way, but of course, as we said before, we can just do in different ways. And this is the sign pattern we decide, right? Probably you can see you have minus, then you have plus, 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 and because this is minus, you have a plus here. This minus, you have plus, plus here, and because this is plus, you have minus, minus. This is standard for this problem. So the first thing is, how are we going to solve the problem? So the way to do it is the following. We know that the sign of the adjoint is just minus 1 to the I plus j, which is depends on the position of the element, times sigma I sigma j, which is this is the sign of our vertex in the graph, right? Sigma I is positive if it's in the I element, and sigma j is negative if you have the minus right here, like sigma 1 is positive, sigma 2 is negative, and so forth, times a tilde ij, right? So ij tilde need to have the sign sigma I sigma j. Okay, this is what we expect to get. Now, the one identity it's really helpful for us is the following. So we have n by n matrix, which is TTP with respect to the tree. So we have for any I, j, and k, whatever they are, just different. Oh, they can be, yes, they need to be different. Then a tilde ki times the determinant of this plus, well, akj tilde of this plus akk tilde determinant of this equal to 0. Here n is just the whole set of numbers of the related with the matrix except the I, j, and k entries that we had. Okay, ordered as we said before. So this is not ordered, right? So we need to move the I into the right place if we want to do something, and the same here. So in this way, this is just equal to 0. This is very cool and really useful. So and we use that to get the result. I'm not going to use right here in the proof of this of the talk, but you can see how we use that in the paper. I will show you also the reference of the paper at the end of the talk. So the way to proceed was the following. We started with two leaves. So you have, well, by the way, you have a tree, of course, at least you have 3 leaves. This is not difficult to see. If you only have 2 leaves, this is because you only have the worm, well, the tree, which is a worm, right? Entry, 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 and only connected with respect to the next one. So there's only 2, but this is very simple case. This is very fast to get. So we know that at least we have 3 leaves. So because of that, this is quite simple to get by using this identity. Okay, so this was the first result. Once we have that, we can just, for any particular leaf P, every matrix, every entry of the matrix of the way A tilde IP has the right sign, as well as A tilde PI, right? IP or PI. So now we have, if we have our matrix, every row which is related with a leaf, all this row and all these columns have the right sign pattern that we expect. Okay, this is not difficult either to get. So the last part is I have any ij in the graph, and I want to get the sign of the I tilde ij, right? This is the last part we want. I'm gonna do it really quick. So in order to do it, let's say this is not true. So this is minus this value. So because the sign is positive or negative. So if it's not this sign, it's negative. Negative this. So but the determinant of A tilde JPIP is just JI here, JP here, PI here, and PP here. So this determinant is just this value. Okay? So we know that this sign needs to be minus this. Okay? So if this is the case, you know, we know that because this condition. Okay, it's not just because we want. It's just to proceed in the way of the hypothesis we used. Now, because the determinant is positive, the sign of this matrix is just the sign of the inverse, but you know, this sign is positive, times the sign of the inverse of this, which is minus 1 to the I plus j plus, which is just I plus j, and the determinant of the whole n minus jp, which is njp, and the whole set minus IP, which is NIP, right? So this is the whole element, the whole entry, 1 to n, without J and P, and this is without I and P. All right, so because of that, what is the sign of this? Well, the sign of this, because this is a bracket, this is just, we don't have the P in our set, so this is the determinant of AP ij. Okay, you see, we are removing two elements, but in this case both are P, so we can have the submatrix AP. But this matrix, this matrix satisfies the condition of the problem, which means that the determinant of this matrix has the right sign. So this is going to be sigma I, sigma j, okay? Because this is this dead joint. So this number is positive, but we expect to have a negative value, well, here, right? So, and because they have different values, this is a contradiction. So that's it. So they have the right sign. The sign needs to be sigma I, sigma j. So with this, we have the whole thing proved. So we know that our matrix has the right pattern for the eigenvector for the last eigenvalue, for the smallest. Okay, so the proof only works, only works for, for the settings we consider. So let me show you some particular cases for which we have some trouble trying to get the result. So we have this matrix with respect to this graph. This is called pitchfork. So you see, in this case, we only know that the submatrices 1, 2, 4, 5 and 1, 3, 4, 5 are TP. Okay, well, but we also have 1, 2, 3 here, but we don't have, we have the determinant is negative for this particular matrix, and we also have, because 5 is pendant, and well, 2 and 3 are pendant, are leaves, this determinant is going to be is negative, so it doesn't apply. It's not true that the A5 is a P matrix. So for this case, this is the smallest eigenvalue, and the eigenvector for that, we have the 1 here, but we expect to have, if we have this negative here, positive, which is positive, but we expect to have negative here, but we have a positive value. All right, so you see, some cases it doesn't work, but it doesn't work if you really go far away from the high degree vertex, like in this case, right? So we need to understand better this. Well, there are more cases that you can consider, but because I don't want to spend more time, if you want to know more about this problem, or you want to have more examples, I will be happy to show you them. Thank you for your attention. And if you want to know more about this problem, you have these two references and the references therein, where you can see other works for which you can understand better this problem, how to attack in different settings.